Now that we looked at how Apache Cassandra writes data, let's turn around and see how Apache Cassandra reads data. It's a little bit more involved than what we saw in the last video. By the way, we called the previous section the write path. This is the read path. In the last video, we saw that Apache Cassandra writes data to the mem tables and then eventually flushes that data down, making SS tables. So your data is actually spread out amongst several SS tables and also the current mem table. When Apache Cassandra reads, it must coalesce all the values from the SS tables and also the mem table. No big deal. Let's first look at how Apache Cassandra reads data from the mem table. Here is our mem table. Notice we have three partitions. The top one is partition Texas, the next one New York, and the last one partition California. The partition key values are on the left. We have 24, 58, and 83 respectively. Reading data from the mem table is straightforward. All Apache Cassandra has to do is look up the partition by its partition token. In this case, let's look for 58. It's a binary search. Go into memory, find where partition 58 sits, return the value. Not a big deal. Reading from the mem tables is epic fast. SS tables, they're a little bit different beasts. Remember, they're stored on disk. They have file offsets. The partitions are stored in the file, and the partitions don't all have the same length. Here we have partition 7, 13, 18, so on and so forth. What we have at the top here are the actual file offsets where those partitions lie within this SS table. So 7, since it's at the beginning, lies at byte offset 0. Partition 13 is at byte offset 100120, so on and so forth. If you look at your SS tables on disk, you'll notice there are several other files. One of those files is the partition index. It literally acts as an index similar to what you would see in the back of any good book. On the left, we have the partition tokens. On the right, we have the actual byte offsets where the partitions reside in the SS table. Let's do a read. I want partition 58. Go to the index. Notice partition 58 resides at byte offset 7192. Seek to that location inside the SS table file, stream the data directly out of the file, and return the value in order to be coalesced with the other values pulled from the other SS tables and the mem table. Now this is fine and dandy, except SS tables can have several partitions in them depending on your data model. And some of these partition indexes can get rather large. Thus, they're actually stored on disk instead of in memory. So what Apache Cassandra actually does is builds another index on top of your partition index. This is called a partition summary. The partition summary resides in RAM. The values we added to the left of the partition index are the byte offsets inside of the actual partition index. Assuming each record takes 8 bytes, partition with a token of 7 starts at 0. In comes a read request. We're looking for a partition with a token of 36. That falls in the range from 21 to 55. So Apache Cassandra keys off of that byte offset 32 to actually do a lookup inside of the partition index, which is sitting on disk. Apache Cassandra opens a partition index, seeks to that byte offset, and starts doing a search from there. Well, we're not looking for a partition token of 21, so it moves on to the next one. Ah, there's 36. It relies at byte offset 6224 inside of the SS table file. Apache Cassandra opens the SS table file, does a seek, streams the data off disk, and returns it for coalescing with the other values. At that point, if you have it enabled, Apache Cassandra actually has a key cache, which is also an in-memory data structure. After we did all that rigmarole to find the value that we're looking for, which in this case is token 36, byte offset 6224, there's a good chance that the user may do that read or some other similar read later. It's typical caching algorithms. So Apache Cassandra stores the result of that previous read in the key cache, if you got it enabled. The next read comes in, hey, I need partition with a token of 36. Apache Cassandra says, oh, we've seen that partition before. I know exactly where it resides. We skip the whole partition summary and partition index, go directly to the SS table file, stream the data off disk, and return it. There is another optimization sitting on top of all this reading rigmarole. It's called the Bloom filter. You can Google this algorithm. It's actually super awesome. But its job is to say, hey, the data's there, or it's not there, or I can't really tell. Let's look through this. Here we ask for partition 36. We know that partition 36 is in there. The Bloom filter reports, hey, it could possibly be in there, and then the read continues on through the partition summary and the partition index as we saw on the previous slide. Here's another request. I want partition with the 48. The Bloom filter says, not there. The Bloom filter is not responsible for where that data could possibly be, or if it's not there, it just says, yo, I know it's there or it's not there. Here comes another request, partition 74. Sometimes the Bloom filter can't tell whether data is actually there or if it's not there. So in that case, the Bloom filter reports, unknown. It could possibly be there. And then we go through the partition summary and the partition index. If this happens and that token's actually not present, that's called a false read. Ideally, we're not going through the partition summary and the partition index to go look for data that's not there, but sometimes you get these false positives. And you can tune this. If you're willing to trade off some space, memory that is, then you can get more accurate Bloom filters. Totally configurable, no big deal. Now, if you're using the open source Apache Cassandra, everything I told you is still true. However, if you're using DataStax's distribution of Apache Cassandra, we have some wicked sweet optimizations in there to make your reads perform much faster. First of all, there's no longer a partition summary. We don't have that in memory. We still have the partition indexes, but we changed that to be a trie-based data structure. If you Google trie-based data structure, there's a lot of information out there. It's also a sweet algorithm. The thing to take away from this is it's built like a tree. Yes, some people call tries trees, and they're very similar data structures. But since it's a tree-based or trie-based, it looks like a tree type of data structure, the lookups are extremely fast. If your SS tables are large, which most likely they will be, you will see huge performance gains if you use DataStax's distribution of Apache Cassandra. If you're migrating from open source Apache Cassandra to DataStax's distribution of Apache Cassandra, no big deal. What DataStax's distribution of Apache Cassandra does is it'll read your old SS tables as you had them with the open source version and convert them to the new version as it does compaction. We cover compaction in a different section. All right, the read path. A little bit more involved than the write path, but still not that daunting. Let's give you a little bit of hands-on experience with this exercise.